Hi, my name is Finn and welcome to this video on the chemistry of plasticizers. Plasticizers are a kind of small molecule which we add to polymer plastics to make them soft and flexible rather than hard and brittle, so we don't break them so easily. In this video, I'm going to talk about the chemistry of plasticizers. What are they? How do they work? Why are they such a big deal? All that junk. But in order to understand plasticizers, we first need to understand a really important property of polymers called their glass transition temperature. So let's get into it. Polymers are a type of macromolecule made from repeating units called monomers bonded together. A really common example is PVC, or polyvinyl chloride. As you can see in this reaction diagram, many chloroethene molecules react together to form a long-chain polymer. This long-chain polymer is PVC. We use polymers in almost every aspect of our day-to-day lives. Think plastic bottles, lycra clothing, wire coatings, your phone screen. This is because polymers have such diverse properties. For instance, in the examples I just mentioned, lycra and wire coatings are flexible, but plastic bottles and phone screens are brittle and easy to break. This is due to the glass transition temperature of these polymers. Essentially, polymers can exist in two different solid states. The glassy state at lower temperatures, which is the rigid, breakable state, and at higher temperatures, the rubbery state, which is flexible and more difficult to break. The glass transition temperature is the point at which the polymer transitions from the glassy state to the rubbery state. As you can see from this graph, the glass transition temperature is different from the melting point. This is because the transition from glassy to rubbery occurs when the polymer chains have enough energy to move within the solid. They are still ordered and intertwined, so not a liquid, but they have partial motion, so the solid is flexible. So what affects the glass transition temperature? Firstly, the flexibility of the polymer itself. If the backbone contains lots of double bonds or aromatic rings which can restrict the molecule's movement, or rigid side chains which can restrict the chain's ability to move over each other, the chains will require more energy to move freely, and will therefore have a higher glass transition temperature. Secondly, the strength of molecular interactions. You will have learned about van der Waals interactions and hydrogen bonding while learning about melting and boiling points. And the same is true of the glass transition temperature. So longer chain polymers, polymers with stronger permanent dipoles, polymers with elements that can hydrogen bond to a neighbouring molecule, all of these will have stronger intermolecular interactions and will therefore require more energy input to overcome those interactions, resulting in a higher glass transition temperature. Alright, so where do plasticizers come in? Adding plasticizer molecules to a polymer disrupts the order of the polymer chains, making it easier for them to move over one another. This means plasticizers can lower a polymer's glass transition temperature. This means if a polymer is in the glassy state at room temperature, the addition of a plasticizer can allow it to exist in the rubbery state at the same temperature, if it lowers its glass transition temperature significantly enough. For example, many children's toys are made of PVC, since it's one of the most readily available plastics in the industry. However, the glass transition temperature of PVC is 82 degrees, so it's in the glassy state at room temperature. But we don't want children playing with brittle, breakable toys with sharp edges now, do we? This is why we use plasticizers in children's toys. Most notably, a family of plasticizers known as phthalates used to be extremely commonly used to soften PVC toys, especially DEHP, or di-2-ethyl-hexyl phthalate. Unfortunately, there is evidence from animal testing that DEHP can in fact damage the liver, kidneys and reproductive organs of children in high enough concentrations. So the use of DEHP in toys was banned in the EU in 2004, despite a lack of concrete evidence that DEHP can actually be found in harmful concentrations in toys. The issue is this. DEHP forms hydrogen bonds with surrounding PVC molecules, like so. But hydrogen bonds are not as strong as covalent bonds, so DEHP is prone to a process called leaching. DEHP molecules can diffuse out of the network of PVC molecules and into the surrounding environment. So if the surrounding environment is a child's mouth and the leaching process is sped up by the child chewing or sucking on the toy, that's a problem. Since PVC is the major player in the plastics industry, a lot of research has since gone into reducing plasticizer leaching and into non-harmful phthalate alternatives. For instance, the idea of internal plasticizers is promising. This means that rather than the plasticizer just being integrated into the material through hydrogen bonding and other molecular interactions, it is actually covalently bonded to a polymer chain. Since covalent bonds are significantly stronger than these molecular interactions, the plasticizer is more easily retained in the material, so the problem of leaching is greatly reduced. Alternatively, there's research currently going on about coating materials which surround a PVC component and prevent plasticizer from diffusing out into the environment, though this is less applicable for children's toys and more useful in, for example, medical PVC tubing. Here's an example of such a coating. This compound is called PCB. PCB is a zwitterion. That means it exists with both a formal positive charge and a formal negative charge at the same time. And it's also a polymer. When PVC is coated with PCB and zapped with a little UV radiation, the positive and negative charges on different PCB molecules can react, forming a cross-linking web of polymer chains. This cross-linking prevents plasticizer leaching out of the underlying PVC, since it physically cannot fit through the gaps in the cross-linked web to diffuse out. This particular study showed that a PCB coating could reduce DEHP leaching by over 85% in a 24-hour period. That's a pretty incredible decrease. So what have we learned about the chemistry of plasticizers? They're additives which decrease the glass transition temperature of polymers, making them soft rather than hard and brittle. Some, like DEHP, are slightly toxic, and there have been controversies in the past over their use, especially in children's toys. And finally, researchers are currently doing a lot to keep plastics and their additives safe for everyone. Alright then, that's all from me about plasticizers. Personally, I think polymers are really cool and really important in our everyday lives, so I hope you enjoyed this video and that you learned something. Thanks for watching.